So before we see more examples on Stokes theorem, remember Stokes theorem was somehow a relation between the surface integral over a surface and the curve integral of the opening curve of that surface. So this was the statement of the theorem. Remember, to apply the theorem, we said we must have an open surface, not a closed surface, unlike the divergence theorem, unlike the Green's theorem for closed curves. We did one example where we had the disk and we did some clarifications for the normal vector orientation. We had all of this. Now, before seeing more examples, I like to mention one remark. So let's see be any closed curve in R3. So imagine you have a curve like this. It could be a circle, anything, just a curve like this. Oriented in any direction is not a big deal now. Okay. So imagine you have a circle, just to make things clear. Now, if you agree, this circle, it can be the opening curve for a hemisphere. So if this is a hemisphere, so let me call this surface S1. Let me call this curve C. So if you agree, according to the Stokes theorem, if you take the integral over C f dot dr, again in a certain orientation, a certain direction, that's not my goal now, it will be equal to the surface integral over S1 f, curl f, curl f dot n dA. Okay? Now, for exactly the same curve C, if you agree, I can have like, let's say, a cylinder, a closed cylinder from the top, like this, and this is closed. And if you look at this cylinder, so if you forget the red part, if you forget S1, the hemisphere, if you just look at the green surface, the cylinder, the opening curve for that surface is also C. So if you apply Stokes theorem for that green surface, you will have the integral over C f dot dr. Again, there is a certain orientation, yes, equals the integral of curl f over C2. This is, over S2, this is S2. So basically, because these two sides are equal, these two sides must be equal. So what is the remark? What is the remark? So the remark is, if you have two surfaces, if S1 and S2 are two, let me say, open surfaces sharing the same opening curve C, and of course, if f is smooth, then what? The two integrals over S1, S2 are equal, but so the integral over S1, not of f, but of the curve. This is a very nice remark. So in general, what happens is this. Imagine you have a curve, any curve. So this is your curve C. Now this curve, it could be the opening curve for a surface like this, an arbitrary surface. Just imagine this in R3 like a surface. It could be the opening of another surface like this, S2, this is S1. So what this remark says is that if you take the curl of the function, the surface integral over the two surfaces are equal. Very nice, very nice. So what we are saying is that the surface integral of the curl does not depend on the surface, right? So it just depends on what? It just depends on the opening curve. So if you know the values of the curl over the opening curve, that's enough for you to compute the integral over the whole surface. It's a very nice result. And this reminds me of something related. Remember, just to make things a little bit connected, so let's remember something. In calculus, just in calculus, you have the integral from a to b, f prime of x dx. What was this? You integrate f prime, you get f, then you just substitute f of b minus f of a, right? So what's the relation between the two things? What's the relation between the two things? You have an interval ab. You have many values. Between a and b, there are infinitely many numbers. A plus b over 2, a plus any convex combination of a and b. So you have infinitely many values between a and b. You're integrating a function over this whole interval. But in the end, the final answer depends only on the value of f at b and the value of f at a. So if you just know the value of f at this point and at this point, that's enough for you to compute the integral. It's very nice that the whole value depends only on the boundary. Look at a and b. A and b, they represent the boundary of this interval. It's like the same thing here. This curve C here, it is what? It is the boundary for the surfaces. So if you have two surfaces sharing the same boundary curve, you get the same thing. Not only this. Also recall the very similar stuff from the curve integral. So by big A, big B, I mean a point A, a point B. So the A, for example, this is A, some point in R2 or in R3, this is B. If you have a curve C from A to B, remember, if f was conservative, so if big F is the gradient of some little f, then the curve integral of the gradient was what? It was f at the terminal point minus f at the initial point. So again, you're taking a curve C, an arbitrary curve C, you're doing an integral, and in the end you're saying that this integral does not depend on the curve. So although you have infinitely many choices of curves, on each of these curves you have infinitely many points, the final answer of your integral only depends on what? Only depends on A and B. So again, you're saying that the integral depends on the boundary. If you look at A and B as the boundaries of this curve, somehow the value of the integral depends only on the values of f at those boundary points. This is somehow related to what we're saying here in this remark, that if you have two surfaces with the same boundary curve, you get the same surface integral. Of course, if you are integrating what? The curl of f, the curl of f. Like here, it's not any function, it has to be a gradient of a certain function. Also for this, it has to be a derivative of a certain function. If it doesn't satisfy this form, of course the formula is not valid. Okay. So let's continue with the Stokes theorem and another example. So let's take, for example, a function, and in this example I'm not taking a function with curl equal to 0. So let's take, for example, y squared z cubed and x. This is my function, and let's take let us be the upper half of the unit sphere. Again, I want to show you how to verify Stokes theorem of course, for this function and this surface. So in this example, the surface is the upper half of the hemisphere. So this is x squared plus y squared plus z squared equals 1. The upper half means that z is bigger than or equal to 0. So in this example, this is the x, this is the y, this is the z axis. Okay. Of course, for our opening curve, this is the opening curve. And what is the equation of this opening curve? Because this is exactly the intersection of the sphere equation with the xy plane. Of course, the intersection occurs when z equals 0. So if you plug 0 into the sphere equation, you will get x squared plus y squared equals 1, of course, when z is equal to 0. Okay, so again, we need to verify Stokes theorem, which means we need to compute the curve integral and the surface integral. Now, what is the orientation? What is the orientation of the curve and the surface? Remember, for the surface, the orientation is easily understood. It's just the direction that you are moving in. While for the surface, the orientation means the direction of the normal vector. So for the hemisphere, the normal vector could be the upward or the downward. So if you take any point again, if you take any point on the sphere, remember in this example we had the desk. It was like a different example. So now if you take this hemisphere and you take any point on the hemisphere, the normal vector is either the outward normal vector or the inward. I'm not going to draw it. So if we take this one, again, if you take this normal vector, you are allowed to do it, but then taking this normal vector orientation forces you to take a certain orientation for the curve. So now if you take this, what's the appropriate orientation for the curve? Imagine you are one of those vectors. You are looking down to this watch here. This is the curve. And you're saying, okay, I want this curve to be oriented counterclockwise. Again, counterclockwise will be like this. It will be exactly like this. So now the idea is, okay, we compute, so for the integral over C, so how do you compute the integral over C? What is your curve? This is again my curve, and it's very similar to the previous example. So the orientation will be cosine t, sorry, the parameterization, sine t0. You will need r prime of t, which is minus sine cosine 0. Then the integral over C is the integral from 0 to 2 pi. You substitute f into your function, then dot r prime dt. This is r prime. So now if you substitute the parameterization into your function, the y square will be sine square, the z cube will be 0, and the x will be cosine t. And nicely, what you get is minus sine cube plus 0 dt. You get 0 again. If you integrate sine cube, remember the sine cube, this is the sine function from 0 to 2 pi. So half of it is positive, the other half is negative. When you cube it, the signs stay the same. So the positive stays positive, the negative stays negative. So basically, when you do the integral over 0 to pi, you will get 0. So this is the curve integral. Now what about the surface integral curl f dot n dA? Okay. So this time we want to compute a surface integral. So to compute a surface integral, of course we need to find the curl. Then this is my surface. So now I'm not talking about the curve. It is an open surface. So we need to do like a parameterization of the surface and so on. So in the first place, we compute the curl. So what's the curl? It's nabla cross f, which is I, j, k, d by dx, d by dy by z, and then you take your function, which is y square c cube x. Now you compute this determinant. So what is with I? With I, this is minus 3z squared. What is with j? The j has a negative sign already. Then it's so it's negative 1. What is with k? It is minus 2y. So this is the curl. So in this example, the curl is not 0. So the computations are not, just to remind you, in our previous example, we had a function where the curl gives us 0, so the integral of this over the surface was right away 0. Now we have some computations, but in the end, the answer must be 0. We know it from Stokes Theorem. Okay, so this is the curl. After having the curl, now we need to find a parameterization for S. Now what is S? S is the hemisphere. Now at this point, if you like, of course, we can use this remark. So remember this remark: if you have two surfaces having the same boundary curve, integrating the curl over these surfaces give you the same value. So if you look at our example, what is my surface? My surface is the hemisphere. This hemisphere has an opening curve C. This is the curve C, it's in red, okay? Now what about if you take the easier surface, you just take this disk. If you take this disk, what is the opening curve for that disk? It is the same red curve. So this sphere and this disk, they have a common curve C. So according to this remark, if you integrate the curl over S1 and S2, you get the same value. So we can do it. So this is where Stokes theorem and the computations become really interesting. So you need to find a parameterization for S, but remember, S, the original surface is a sphere. So you need to deal with spherical coordinates, spherical parameterization, and that cross product and so on. So instead of doing it, so using our previous remark, what we can do is, okay, we can replace S by, let me call it S1, which is what? We can replace, replace S, the hemisphere, by S1, which is what? Which is all points satisfying this inequality. So x squared plus y squared less than or equal to 1. This is the disk at the level z equal to 0. This is much easier than the sphere. So now if you find the parameterization, which is the polar parameterization, x is r cosine, y is r sine, and z is 0. Again, if you compare this, just make a comparison. Just compare with the parameterization of S. It will be really easier because S is a sphere, so the parameterization follows the spherical coordinates. It's a way more complicated than this. So this is R of R and theta. Then you need to compute a normal vector. What's a normal vector? It's R sub R cross R sub theta. So you have the I, the J, the K. What is R sub R? It is cosine theta, sine theta 0. What is R sub theta? It's minus R sine R cosine 0. If you compute, it will be 0, 0, and R. Okay? Okay, so now we took our, so this was our curve C. So this is our surface. Again, we replaced the hemisphere by this easier surface. And now we computed the normal vector. 0, 0, R is the upward normal vector. Remember, when we had our curve computations, what was the orientation? This was the orientation. So it's the counterclockwise. And this is still consistent. With the orientation of our surface. These blue normal vectors, if you imagine yourself standing here looking at the red curve as your watch, these arrows represent the counterclockwise orientation of this surface. And now you just compute the surface integral of the curl, which will be double integral. Now the curl, you take the curl into here, dot the normal vector, but the normal vector is 0, 0, r, dr, d theta. So regardless of what you have here, you will get zeros. So what's significant is only the third coordinates of the curl. So if you look at the curl, these are the curl computations. The third component was negative 2y, so it's negative 2y. What is y from my parameterization? It's r sine theta. The theta is from 0 to 2 pi. The r is from 0 to 1. Now if you do these computations, you will get 0 to pi, 0, 1, minus 2 r squared sine theta, dr d theta, and again, because of sine theta, the integral will be 0. Again, this is the verification of Stokes theorem, and this is how we used our remark about the equality in this identity, the equality of the surface integral of two surfaces sharing the same boundary curve. So in this example, we replaced the hemisphere, the original surface, with a much easier surface, that is the disk.